Okay, so let's look at example number 2, which is use first principles to differentiate, right, to get the derivative of y equals x cubed minus 4x. So to use first principles, if you remember the equation used f of x in the equation, and it also used f of x plus h in the equation, right, and then divided by h. But this has y equals. So I would say first, let's just change this equation into function notation, and instead of y equals, make it f of x equals x cubed minus 4x. Not a big deal, but in order to be using this equation with f of x in it, we should make sure the original equation is in function notation, right? So what I need to do then is have, again, f of x is just going to be the original, but I need to find f of x plus h. So let's just over to the side here, find what f of x plus h is going to be. So again, whenever I see x in my original, or I should use this one here, I put x plus h instead. So x plus h cubed minus 4 times x plus h. And so I could solve x plus h cubed by simply doing multiplying the binomials. So by having x plus h multiplied by x plus h multiplied by x plus h, where I can do the first two and then multiply in the last term afterwards. I can write down the first term here and then multiply using FOIL those and then multiply that into my answer later. Or if you do remember Pascal's triangle, using binomial expansion is just a little bit of a shortcut. Obviously, we're going to get the same answer. So we will have an answer of x cubed plus 3x squared h plus 3x h squared plus h cubed. And just make sure that's done right. X cubed plus 3x squared h plus 3x h squared plus h cubed. And then minus, that's just the beginning part, right? Then we have to use distributive property here to do the negative 4 times x and the negative 4 times h. So then we have negative 4x minus 4h. Okay, and is there anything to clean up or simplify here? I have a cubed. This is squared on the x, this is squared on the h, so they are not like terms, right? It's same variable and same exponent. They're not the same exponent on the same variable. X and h, same thing, different variables. That's my whole long thing. I can't simplify that any further. So then if I go over here and write out my equation for the derivative, f prime of x is equal to the limit as h approaches 0 of f of x plus h, right, minus f of x. We should pretty much have it memorized by now, all over h. And let's go. Again, we're going to write down the limit as h approaches 0 until I am subbing in 0 for h. So until that moment, I'm going to write that down every time. So I have my f of x plus h, this whole thing here. So let's just make sure we're writing it down properly. So just go slow. X cubed plus 3x squared h plus 3x h squared. I think I should have wrote it a little bit lower. So just excuse me if it starts to angle down a bit. Minus 4x minus 4h. Take away, so that's just f of x plus h. When I take away, I'm going to put a bracket. What is f of x? Take away x cubed minus 4x. This whole long thing, all over h. Then the first thing I would do is distribute the negative in. So it's going to be this whole long thing again. But then in that same step, I'll be canceling, hopefully, some things out, right? So I'm copying out this whole part again. X cubed plus 3x squared h plus 3x h squared plus h cubed minus 4x minus 4h minus x cubed plus 4x, because negative and negative become a positive, all over h. Let's get my different color, or hopefully you have different colors with you. Okay, well, I've got some things going here. I can see an x cubed and a negative x cubed. I have a negative 4x and a positive 4x. H, no, I think that might be it, but hey, we got rid of some. So let's rewrite what we have now. So the limit as h approaches 0 is 3x squared h plus 3x h squared plus h cubed. Let me just check my notes here, make sure everything's on track. Minus the leftover here for h, don't forget, all over h. And then what we want to do is factor out the h, so we can get rid of h as the denominator, because h cannot be 0 as the denominator. Since I'm typing in h is 0, that's not going to be good, right? So factor out the h of every single term. So then I'm left with 3x squared plus 3xh. Again, plus, we're taking out just one h, so h squared minus 4 all over h. We're getting there. And cross out, cross out. So therefore, my limit as h approaches 0 is 3x squared plus 3xh. I want to make sure this is written down properly. Plus h squared minus 4. Okay, now I've gotten rid of my denominator. Now I can replace the h's with 0. So now that I'm replacing the h's with 0, I don't need to write down the limit or as h approaches anymore, right? I can just write down 3x squared. Don't accidentally put it in for x, right? It's only the h's. X we need for our equation. Plus 3x times 0 in for h, plus 0 squared in for h minus 4. So 0 squared is just 0. 0 times x times 3 is just 0. So it's getting simplified. So I'm left with 3x squared minus 4. So that is my derivative equation, my derivative function. Or, so I could write it as, I should be writing it as f prime of x, right? Saying that it's a derivative equation equals 3x squared minus 4. Or if we were to look up here, since it started originally with a y, and just to get used to the other notation, right? Or I can write it as y prime, right? To go back and relate it to the original, 3x squared minus 4. So use first principles to differentiate. Differentiate means find the derivative, which we found the derivative. Here's both. Either equation I could have finished off with. The derivative equation is 3x squared minus 4. And that derivative equation is giving me an equation that represents the instantaneous rate of change at different x values. So when I plug in different x values here, values for x, in this question I don't have to, but if I was given to do that, then I would know what the equation would be. So let's go to the next question. Now the next question is asking us to use first principles to prove that the derivative, to prove that when I get the derivative of f prime at 2, so at that point 2, when I get the derivative and I'm subbing in an x value of 2, that derivative does not exist for this function, for these equations here, which is one function altogether, right? So in order for something to not exist, it either needs to be discontinuous, right? At that point, not the whole entire graph function, but at that point, or it's continuous and there's either a corner or a cusp happening. So first of all, I can see here that these are abrupt changes. Because I can see that this is negative x plus 5. So that looks like y equals mx plus b. M is negative, which means that my slope is decreasing all the way up until the point of, oh, 2. That's not a coincidence, right? Up to and including 2. And then greater, when x is greater than 2, I'm following this equation, which is 0.5x plus 2, which is also y equals mx plus b. It's also a straight line, but my slope is positive and my slope is a little smaller, so not as steep. So then I'm going in a positive direction, trying to make that look a little less steep, but really with the numbers of -1 and 0.5, you probably wouldn't even barely see it with the eye. So it looks like I have a corner here. It looks like it's just to go over, it's a continuous graph, right? Passes the vertical line test. It's a continuous graph, but we're talking about a corner here. And so at that corner, which go figure, at that corner is at the x value of 2, right? Because it goes all the way till x is less than or equal to 2 on the left-hand side, and then on the right-hand side, the change is happening at 2. So at 2, we're trying to prove that it doesn't exist. So if I'm thinking about it firsthand, it does make sense that that the derivative is not going to exist at that point, right? But it is, the limit exists. Well, let's take a look. The limit exists. Let's take a look. Let's find out the limit just to understand a little bit further. Let's find the limit as x is approaching that 2 from the left-hand side. So if x is approaching 2 from the left-hand side, I'd be using x is less than or equal to 2, this equation, -x plus 5, and then all I do is sub in the value of 2. So -2 plus 5, and I get a value of 3, right? So this is approaching 2 from the left-hand side. X is approaching 2 from the left-hand side. My limit is 3, so I'm nearing a y value of 3. Do I have room? Because I don't want to take up room down here. I'm going to kind of just squish it, guys. It's not going to look good, okay? But just bear with me. So the limit is x approaches 2 from the right-hand side. Well, which equation am I using? So if I'm coming in from the right, I'm coming in at numbers greater than 2. Right? I'm starting at 5, 4, 3, and narrowing in on 2. So I'm going to be using this equation, 0.5x plus 2. And then I'm just going to bring that down here. So 0.5, my x is 2 plus 2, which is 1, right? Half of 2 is 1 plus 2. Oh, look at that. As I approach 2 from the left-hand side, I'm nearing a y value of 3. As I approach 2 from the right-hand side, right, I'm nearing a value of 3. So that means that the limit exists. I'm going to write that over here so I don't take up paper space. So that means that the limit exists, right? So that means that there's a closed hole there, which is what I drew anyways, but there's a closed hole there. So the limit exists. It's a continuous graph. The limit exists, but we're trying to prove that the derivative does not exist because we have that one exception that it's a corner, or if it was a cusp. We know it's a corner because we know the lines are straight, because we know that they're linear equations here, right? So now let's get to using first principles. I'm just trying to figure out how to best section this off. Okay, just so that we are seeing this better. So let's write out our equation. So f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So if I'm trying to prove that the derivative at 2 does not exist for the following function, I need to approach it from the left-hand side. I need to have an answer. And then from the right-hand side, I need to have an answer. So let's do the left-hand side first. So the limit as h is approaching 0 from the left-hand side, so as h approaches 0, but from the left-hand side, my x value, I'm going to plug in what it wants me to. My x value is 2. So here in my equation, I'm just going to plug in x equals 2. So that changes the original equation to f of 2 plus h minus f at 2 all over h. So now I have, what's my equation? When I'm approaching from the left, remember, I'm approaching from the left, I was using the negative x plus 5 equation when I'm approaching from the left. So I'm going to use my negative x plus 5 equation for f of x. So here I have my limit as h approaches 0 from the left, still mentioning from the left. So starting with this original equation, negative, and my x value is now 2 plus h plus 5 minus bracket f at 2. So minus x plus 5. So negative 2 plus 5 all over h. Okay. So is there any simplifying that I can do here? So that's going to equal negative 2 minus h, distributive property. You're kidding me, right? Okay, is it still going? That is very strange. Very, very strange. I don't know. I'm gonna have to go back and see if everything is recorded here. Okay, well, I don't know what happened there. Internet connection is what it looks like, but I'm just gonna continue on because I'm almost at the end of the video rather than going over again. So I was at here, the limit as h approaches 0 of negative 2 minus h plus 5 positive 2 minus 5 divided by h. So then I would have negative 2 plus 2 and 5 minus 5. So I end up with negative h over h, which sure I can write that out. So I end up with negative h divided by h, which is going to be equal to negative 1. So the limit as I approach 0, from the left-hand side, is negative 1. I'm going to be nearing a y value of 1. So now I need my limit as I approach from the right-hand side. So my limit as I approach 0, but from the right-hand side, so from the right-hand side, right, I'm going to be using this equation, 0.5x plus 2, because I'm approaching from the right-hand side. So I have my original still, f of, remember I take my x and I sub in 2 because it's giving me x is 2, so 2 plus h, so instead of x plus h, minus f of x, but x is 2 over h, and then I plug in my equations here. So I'm using now the equation 0.5x plus 2. So now I have equal to the limit as h is approaching 0 from the right of, where are we here, of this equation first. So 0.5 then x, so 0.5 then x is 2 plus h plus 2, finishing off this equation, minus f at 2. So minus this equation and plugging in f at 2. So 0.5 times 2 plus 2 over h. Then simplify. I'm not subbing in. My h's are 0 yet. So I have to keep the h approaching 0 from the positive side. So now I have distributive property. What's half of 2? Half times 2 is 1 plus 0.5h plus 2. And then half times 2 is 1. Negative times 1 is negative 1. And negative times positive 2 is negative 2. And is that going to condense down at all? Let's see. 1 minus 1, 2 minus 2 Okay, so it very much does. So then I have 0.5h divided by h. So I have an answer of 0.5. So if we see, if I'm approaching 0 from the left-hand side, I get an answer of -1. If I'm approaching 0 from the right-hand side, I get an answer of 0.5. So remember, for the limit to exist, both sides of the limit have to equal the same value. They both have to be nearing the same y value, and they don't. So since the left-handed limit and the right-handed limit are not equal, then the derivative does not exist at x equals 2. So we should probably write that down. Let's see if I can fit it in here. So since, because this is what I would want you to write down for me, since the left-handed limit and right-handed limit since the left-handed limit and right-handed limit are not equal to each other, the derivative does not exist at x equals 2. Here we go.